All right, we've covered the theory. We understand what machine learning is, how data flows through a pipeline, and the math behind it. Now it's time to bring it all together. Let's build our first machine learning model. We'll start with simple linear regression. One input, one output, one straight line. The simplest form of regression there is. Once we understand this well, we'll extend it to multiple linear regression, where the model takes in many features at once and learns a weight for each one. But first, simple linear regression. Let's make this concrete with a real example. Imagine you run an ice cream shop. Every day, you record two things: the temperature outside and how many ice creams you sold. That's your data set. Temperature is the input. Ice cream sold is the output. And even just glancing at the table, a pattern starts to emerge. On cooler days, sales are lower. On hotter days, sales climb higher. As temperature goes up, sales go up too. But can a machine learn this pattern on its own? That's exactly what we're going to find out. Before we build the model, let's be clear about the problem it's trying to solve. We have recorded data for multiple days, temperature and ice cream sales day after day. But what if we want to predict something we've never recorded? What will be the number of ice creams sold when the temperature is 35 degrees? We can't look it up. It's simply not in our data set. But here's the thing. The pattern is already there, hidden inside the data we do have. If we can learn that pattern, we can predict any temperature, including ones we've never seen before. And that's exactly what a regression model does. Looking at the scatter, we could make several reasonable guesses. Maybe 310, maybe 335, maybe 360. All of them seem plausible, but which one is right? This is exactly the problem. We don't want a guess. We want the best possible estimate, one that's informed by the entire dataset, not just the few points near 35. And the way we get there is by finding a line. One line that runs through the whole cloud of data, capturing the overall trend from every single point. Once we have that line, predicting 35 degrees becomes simple. We just find 35 on the axis, follow it up to the line, and read off the value. That's the line we need to find, the best fit line. So how do we actually find the best fit line? We start simple. We draw any line through the data, just something that roughly passes through the cloud of points. It doesn't have to be perfect. It's just a starting point. Now the question is, how good is this line? To answer that, we measure the error. For every data point, we look at the actual value, the real number of ice creams sold that day, and compare it to the value the line predicts for that same temperature. The gap between the two, that's the error. The actual value is what really happened that day, the real number of ice creams sold. The predicted value is what the line says should have happened at that temperature. The error is simply the difference between the two. We do this for every single point in the dataset. Every dot gets its own error. Now here's the catch. Some errors are positive. The dot sits above the line, meaning we under-predicted. Some are negative. The dot sits below the line, meaning we over-predicted. If we just added all these errors together, the positives and negatives would cancel each other out. We'd end up with something close to zero, and it would look like the line fits perfectly, even when it doesn't. So instead, we square each error first. Squaring makes every value positive. The sign disappears. Now there's no cancellation. Then we sum all those squared errors together and take the average. That gives us one single number, the mean squared error. And here's the key idea. The best fit line is simply the line that makes this number as small as possible. The lower the mean squared error, the better the line fits the data. That's what the model is looking for. Not a perfect line, just the one with the least average error across all the data. Now let's see how the model actually finds that best fit line. On the left, you can see our equation, y equals w times x plus b. Two parameters control this line completely: the weight w, which controls the slope, and the bias b, which controls where the line starts. The goal is to find the values of w and b that make those errors as small as possible across the whole dataset. That's what training is: finding the right weight and bias. It doesn't touch every dot. It doesn't need to. It runs through the middle of the cloud, capturing the overall trend, not chasing individual points. And that's actually the right behavior. A line that perfectly touches every single dot would be memorizing the data, not learning from it. We want a line that generalizes, one that works for new data it has never seen before. And once the model finds the best weight and bias, it can make predictions. Look at the green marker on the graph. Temperature is 35 degrees. The line gives us a predicted value of around 340 ice creams. The model didn't look this up in the table. It learned the relationship between temperature and sales and used that relationship to predict a value it had never seen before. That's linear regression in action. One input, one output, one straight line. A machine learning a pattern from data. And in the next section, we'll implement this exact model in Python, step by step, from scratch. Now, before we write any code, we need to bring in a few Python libraries. We'll be using a couple of Python libraries to get started. First, Pandas, for reading and working with our data. Think of it like Excel, but in Python. Next, NumPy, for numerical operations and working with arrays of numbers. And finally, Scikit-learn. This is our machine learning library. It has everything we need to build, train, and evaluate our model, all in just a few lines of code. These three libraries are the backbone of almost every machine learning project you'll come across. Get comfortable with them. They'll show up again and again throughout this series. All right, let's open Visual Studio Code. I've already created a folder called Simple Linear Regression. This is where everything for this project will live. First thing, let's add our dataset. Take the CSV file you downloaded from the link in the description and drop it into this folder. That's it for setup. Now let's open a new Jupyter notebook inside this folder and start writing code. Step 1. Data preparation. We start by importing Pandas, giving it the alias PD as a shorthand so we don't have to type the full name every time. Next, we use pd.read_csv to load our CSV file into something called a data frame. Think of a data frame as a table, rows and columns, just like a spreadsheet, but now it's inside Python, and we can work with it programmatically. Then we call df.head to print the first 5 rows. Just a quick sanity check to make sure the data loaded correctly. And there it is, temperature in the first column, ice cream sold in the second, looking exactly as expected. Now, we need to separate our input from our output. In machine learning, we call the input the feature and the output the target variable. We extract the temperature column into x, our feature, and ice cream sold into y, our target. Notice we're using double square brackets here. A single bracket gives us a one-dimensional array, just a flat list of numbers. Double brackets give us a two-dimensional array, rows and columns. This matters because the machine learning operations coming up only accept two-dimensional input, so we make sure x is already in that shape from the start. We then print the shapes of both arrays. Both X and Y show 26 rows and 1 column. 26 data points, 1 feature, 1 target. Data is loaded, separated, and ready. Stage 1, done. Now let's move to the next step, splitting our data into a training set and a test set. Before we write any code, let's understand why we split the data in the first place. Think of it like preparing for an exam. You study from a textbook. That's your training data. But the real test has questions you've never seen before. That's your test data. It's the same with our model. We train it on one portion of the data, then test it on a completely separate portion it has never seen. That's how we know if it truly learned the pattern or just memorized the training examples. Take a look at our dataset. We have 26 data points in total. We'll go with an 80-20 split. 80% of the data goes into training, and the remaining 20% is held back for testing. Now, to do this in Python, we'll use Scikit-learn, a specialized library built specifically for machine learning operations. Scikit-learn is one of the most widely used machine learning libraries in the world. It gives us ready-to-use implementations of dozens of models and utilities, so we don't have to build everything from scratch. Things like splitting data, training models, and evaluating performance are all just a few lines of code. We start by importing train_test_split from Scikit-learn. Then we call it, passing in our features x, our targets y, and setting test_size to 0.2. That tells the method to put 20% of the data into the test set and the remaining 80% into training. The method also randomly shuffles the data before splitting, ensuring the split is fair and representative across the full range of temperatures. And the result is 4 separate sets, x_train and y_train, the training data, x_test and y_test, the test data. The x sets hold our temperature values. The y sets hold our ice cream sales values. Now let's verify the split worked correctly. We print the shapes of all 4 sets, x_train, y_train, x_test, and y_test. The shape tells us how many rows and columns each set has, a quick sanity check to confirm the data was divided exactly the way we expected. And there we go. The training set has 20 rows and the test set has 6. That's our 80-20 split working perfectly across 26 data points. Our data is now cleanly divided. The model will only ever see the training set during learning. The test set stays locked away until evaluation time. Data is split and ready. Now let's train the model. Now for the exciting part, stage 2. Let's train the model. We import 2 things here, linear regression from Scikit-learn, that's the model itself, and matplotlib, a plotting library we'll use in a moment to visualize the result. Now, training a model in Scikit-learn really comes down to just 2 steps. First, we create the model by calling linear regression and storing it in a variable called model. At this point, it's completely empty. No weights, no bias, nothing. Just a blank model ready to learn. Second, we call model.fit, and this is the actual training step. We hand it 2 things, our training features, xtrain, which holds all the temperature values, and our training targets, ytrain, which holds the matching ice cream sales for each of those temperatures. The model now has both halves it needs, the inputs and the correct answers. Its job is to study how the 2 relate and find the line that best connects them. And that's it. That one line is where all the learning happens. Behind the scenes, the model is searching for the weight and bias that give us the lowest possible error across all the training points. We don't write the math ourselves. Scikit-learn handles the entire process under the hood. Now that the model is trained, let's ask it to make predictions on the training data. We call model.predict, passing in xtrain. The model takes each training temperature, runs it through the line it learned, and returns a predicted sales value for each one. We store those in a variable called yTrainPred. Notice the name, yTrainPred. These are the model's predictions for the training data, and naming it clearly will matter in just a moment when we predict on the test data too. Now let's visualize this. We plot the actual training data as blue dots. Each dot is 1 day from our training set. Temperature on the horizontal axis, ice cream sold on the vertical. Then we draw the model's predictions, yTrainPred, as a red line across those same temperatures. Now let's add some labels to make the chart readable. First, we set the label for the horizontal axis, temperature in degrees Celsius. Then the vertical axis, ice creams sold. Then we give the chart a title. We add a legend so it's clear which is the actual data and which is the model's prediction. And here's the result. Blue dots scattered across the graph, with the red best fit line running right through the middle of them. You can clearly see the upward trend the model has learned. As temperature rises, predicted sales rise with it. The model has found its pattern from the training data. But fitting the training data is only half the story. The real question is, how does it perform on data it has never seen before? That's exactly what we're about to find out. So far, the model has only worked with the training set, data it has already seen. Now we give it something new, the test set, 6 data points it has never encountered before. We call model.predict again, but this time we pass in xtest instead of xtrain. And this time we store the result in a separate variable, yTestPred. This is the key distinction. yTrainPred held the predictions on data the model already saw. yTestPred holds predictions on data it has never seen. Keeping them in 2 clearly named variables means we never mix up which is which. The model takes each unseen temperature, runs it through the line it learned, and returns a predicted sales number. No peeking at the real answers, just pure prediction based on what it learned during training. Now let's visualize how those predictions compare against the actual test values. And here's what we get. The blue dots are where sales actually landed. The red line is what the model predicted. And notice something important when you compare the 2 charts. The first chart was packed with dots, all 20 training points. That's the data the model learned from, so of course the line fits it well. But this second chart is different, just 6 dots, and these are days the model never saw during training. Yet the line still runs right through them. That's the real proof. The model didn't just memorize the training data. It learned the actual relationship between temperature and sales. This is what we mean by a model that generalizes. And it's exactly what we want. But a visual is only part of the story. Next, we'll put actual numbers to this and measure exactly how accurate our model really is. Now, stage 3, evaluation. Let's see how good our model actually is. We import 2 metrics from Scikit-learn. Mean squared error, which measures how far off our predictions are on average, and R squared, which tells us how well the model explains the pattern in the data. We calculate mean squared error by passing in our actual test values and our predicted values. Remember what we covered earlier. Mean squared error takes the difference between each actual value and predicted value, squares it, and averages across all data points. The lower this number, the better. Then we calculate R squared the same way. Actual values and predicted values go in. R squared is a score between 0 and 1. A score of 1 means the model perfectly explains the data. A score of 0 means it explains nothing at all. In practice, the closer to 1, the better. Then we print both results. And there are our numbers. two simple metrics that tell us exactly how well our model performed on data it has never seen before. Mean squared error gives us the error in raw numbers, how far off the predictions were on average. R squared gives us the bigger picture, how much of the pattern in the data the model actually captured. Together, these two numbers tell the full story of how well our simple linear regression model learned from the ice cream sales data. So now, let's go back to the question we started with. Right at the beginning, we asked, what will the sales be when the temperature is 35 degrees? A day we had no record of. Now our trained model can finally answer that. We create a small data frame with a single value, 35 degrees, using the same column name, temperature, that the model was trained on. This keeps our input in exactly the format the model expects. Then we call model.predict, passing in that temperature. And we print the result using .item, which pulls out the single predicted number cleanly. And there's our answer. The model takes 35 degrees, runs it through the line it learned, and gives us a predicted number of ice creams sold. This is the whole point of everything we just built. We started with a question about a day that never happened, and our model gave us a real, data-driven prediction. And that wraps up our first complete machine learning model, from raw data all the way to a real prediction. Next, we'll extend this to multiple linear regression, where we add more features and see how the model handles a more complex problem. So let's step back and look at what we just built. Remember the 3 stages every machine learning project follows? Data gathering, model building, and evaluation. We just walked through all 3 in code. Let's recap each one. Stage 1, data gathering. First, we imported our dataset, loading the ice cream sales CSV into a data frame with Pandas. Notice we skipped cleaning and fixing the data. Our dataset was already simple and clean, so there was nothing to fix. But in a later video, we'll work with messier, real-world data, and this step becomes essential. Then we split the data into a training set and a test set. The model learns from one and gets tested on the other. Stage 2, model building. We selected our model, linear regression. Then we trained it on the patterns in our data using model.fit. And finally, we used it to predict on new, unseen data, answering our original question about 35 degrees. And stage 3, evaluation. We verified accuracy on the test set using mean squared error. And we compared against the actual labels with R squared, measuring how well the model captured the real pattern. We skipped tune and iterate this time. Our simple model performed well enough on the first try. But with more complex data, we'd loop back, adjust, and retrain until the results were strong. We'll see exactly that in a later video. And there it is, a complete machine learning workflow, start to finish, in Python. From raw data, all the way to a real prediction. Next, we'll take everything we learned here and extend it to multiple linear regression, where the model works with several features at once.